Hello and welcome to my video. About a year ago, a TV series called Squid Game was released on Netflix. That show made a giant success, and as a South Korean myself, I was quite surprised how well the show has been received around the world. So in this video, marking the anniversary of the Squid Game, I am going to provide a mathematical study on one of the games featured in Squid Game, and that game is Glass Stepping Stones, the fifth game of the contest in the show. Although this game is the least interesting one from a strategical viewpoint because the game is purely luck-based instead of skill-based or strategy-based, it is quite interesting one to cover in a math video like this because we can analyze the game applying important knowledge of probability theory, such as the probability of independent experiments and binomial distribution. So the rules are quite simple. In the show, 16 players, or rather survivors at that point, must cross the 2-panel wide glass bridge with the length of 18 panels, where the panels are made of either tempered glass or regular glass, which are indistinguishable. The tempered glass can support the weight of the players, but regular glass cannot support their weight. So if a player steps on a regular glass, the glass shatters and the player above falls to their death. All players have assigned numbers from 1 to 16, which is the order in which they cross the bridge. So player 1 starts first, then player 2 follows, and so on. In the actual show, there was a time limit, but if we ignore the time limit here, it is obvious that the player number 1 has the worst chance of surviving, while the last player, number 16, has the highest chance of survivor. But can we mathematically calculate those probabilities? In other words, can we find the exact mathematical expression for the probability of each player surviving the game? Of course we can, that's why I made this video, but before we get to the complex topics such as independent trials or probability distribution, let us start from the simplest and easiest part of the problem like in every challenging math problem. Let us first define pk as the probability of player number k surviving by safely passing all 18 pairs of panels. The easiest one to calculate is of course the case of player 1 surviving. In order for player 1 to survive, he or she must pick the correct panel, the tempered glass, 18 times. Therefore, the probability of player 1 surviving is simply 1/2 to the power of 18, which is approximately 0.00038%, which is not a very good chance really. Now let's move on to the slightly more complicated case, the player 2. What is the chance of player 2 survive the game? Well, let us consider all the possible cases that can happen to player 2. First, if player 1 miraculously guesses all 18 correct panels, then player 2 is guaranteed to survive since player 2 can simply follow the exact same path that the player 1 takes. The other case is where player 1 fails midway and falls to the death. Here, if the player 2 correctly guesses all the remaining choices, then player 2 can survive. Otherwise, if the player 2 fails a single time during the rest of the course, then player 2 dies. You can think of these cases like this. From players 1 and 2, if the total number of fails from these two players becomes 2, then player 2 dies. And if the total number of fails is either 0 or 1, then player 2 survives. So when considering the probability P2, we can view the problem as simply choosing the panel between the pair of panels with total 18 pairs. And in order for player 2 to survive, we are only allowed to make wrong choice less than twice. If you want this to be way less dramatic, you can think of this game as the multiple choice test with 2 choices, such as true or false quiz. There are total 18 true or false questions in the quiz, and if you choose the wrong answer less than twice, that's equivalent to player 2 surviving. Therefore, we can now easily notice that P2 is given as probability of number of fails being 0 plus probability of number of fails being 1. Here, the probability of number of fails equals 0 is easy. We have already calculated that, which is the probability of choosing the right answer 18 times. So this term is simply 1/2 to the power of 18. Now let's calculate this term. The probability of number of fails equals 1. Here, we can choose where player 1 should fail, and there are total 18 choices. Or in our true or false quiz analogy, we have 18 questions that we can fail. So the number of cases for the position of the fail is 18. And player 1 must fail in that one particular position. And for other 17 positions or questions, player 2 must succeed. Therefore, we have this expression, which gives 18 times 1/2 to the power of 18. And this gives our final probability, which is 19 times 1/2 to the power of 18, which is 0.0072%. As you can see, this is much higher probability than player 1 surviving. Since many viewers of my channel must be super smart, many of you must have realized how we can generalize the previous results, but let us just do one more time, this time for player 3. The same argument holds for this player as well. In order for player 3 to survive, at most 2 fails are allowed, and if the number of fails becomes 3, then player 3 dies. Here, the first fail means that player 1 picks the wrong glass and dies. The second fail means that player 2 picks the wrong glass and dies. And the third fail means that player 3 picks the wrong glass and dies. Therefore, P3, the probability of player 3 surviving, is given as probability of number of fails being either 0, 1, or 2. Using the previous results for first 2 terms, we obtain this result. So now we have to find out this term. This term is the probability of choosing wrong glass 2 out of 18 times, or the probability of failing 2 questions out of 18 true or false questions. Therefore, the probability can be calculated like this. First, we have to choose 2 positions or questions out of 18, so we have 18 choose 2 cases. In those 2 positions, players 1 and 2 must fail, so we have 1/2 squared the probability of failing twice. Then for other 16 position, whoever player at the lead must succeed all of them, so we have 1/2 to the power of 16, the probability of succeeding 16 times. If we calculate this, we have 153 times 1/2 to the power of 18. Therefore, P3 is given as sum of all of these terms, which is 172 times 1/2 to the power of 18, which is approximately 0.066%. So now the probability of surviving became a bit more higher. Alright, so far we have obtained these results, and from these results, we can now easily generalize the result to player K. Actually, in probability P3, we can write these first 2 terms like this, using 18 choose 0 and 18 choose 1. Now the pattern is obviously recognizable. For player K, the probability of surviving is the probability of number of fails being either 0, 1, 2, all the way up to K-1. Here, the number of fail being 0 means that the player 1 succeeds 18 times, so all the players from 1 to K survive. Next, the number of a fail being 1 means that player 1 fails midway and dies, and player 2 correctly guesses the rest of the challenge so that all the players from 2 to K survive. And the number of fails being 2 means that players 1 and 2 fail and die, and the rest of the players survive, and so on. Finally, the number of fails being K-1 means that all the players ahead of player K fail once and they all die, and only player K survives by guessing the rest of them correctly. And we can also write PK is given as the probability of number of fails being less than or equal to K-1. And using sigma notation, we can write summation of probability of number of fails being I, where I is from 0 to K-1. Now we have to obtain the general expression for the probability of failing I times out of 18 trials. And at this point, it is easy. There are total 18 choose I choices of positions where I players are meant to fail. Then we have the probability of failing I times. Then we have the probability of succeeding the rest, which is 18 minus I times. Therefore, we have this expression. This particular form of probability is often known as probability of independent trials, or the probability of Bernoulli trials. This is the probability applicable to random experiments with exactly 2 possible outcomes, success and failure, in which the probability of success is the same every time the experiment is conducted, which means that the trials are independent. For the general expression, consider an experiment of n statistically independent trials, each with a probability of success p. Then pk, the probability of exactly k successes in these n trials, is given as n choose k times p to the power of k succeeding k times 1 minus p to the power of n minus k, which means failing n minus k times. So this is the general expression for the probability of experiments with repeated independent trials. In our glass stepping stone situation, the number of trials n equals 18, and the probability p of success, or in this case you can also say fail, in each trial is 1 over 2. Hence we have this expression. Now, this general expression of independent trials is quite interesting actually. If we denote the number of success as random variable x, then we have a probability distribution of x. And this particular probability distribution is called binomial distribution. And this expression for probability is called the probability mass function of the binomial distribution. These are all very fascinating and important topics in basic probability theory and statistics, but handling each one of them might be too much for this single video. So let's just get back to our Squid Game situation. Here, the probability of player K surviving is given as the probability of number of fails being less than or equal to K minus 1. This particular expression is called the cumulative distribution function. And we have already seen that this can be also expressed as the summation, like this. So therefore, we have sigma 18 choose I times 1/2 to the power of 18, which in expanded form is this. And this is the general expression for the probability of player K surviving. Now with this general expression, we can plug in the numbers and calculate the actual probabilities of each player surviving. And the probabilities are like this. And if we actually plot this into a graph, we obtain this graph. So you can see that from player 10, players have surviving chance that is higher than 50%, and last two players, players 15 and 16, have more than 99% chance of survivor. So with this calculation and plot of the probabilities, we can easily understand how the probability of surviving changes from player to player. Now, before we go, let us calculate one more thing. What would be the average number of survivors in this game? In other words, what would be the expected value of number of survivors? First, let us remind the mathematical method of calculating the expected value from the probability distribution. If the random variable x can have values from 0 to n, and the probability of x being k is given, which is called the probability mass function, then the expected value of x is given as sigma from k equals 0 to n, k times probability mass function px equals k. Here, our random variable x represents the number of survivors, and the case where k equals 0, which means everyone dies, does not contribute to the expected value. So we only have to consider the case from k equals 1 to k equals 16. Here, the probability mass function px equals k means the probability of exactly k players surviving. So now let's think about this probability of exactly k players surviving. This means that 16 minus k players must fail and fall to their death, so the total number of fails is equal to 16 minus k. And we have already found the method of calculating this, which is given like this, and with simplifying we obtain 18 choose 16 minus k times 1/2 to the power of 18. Therefore, our expected value is given as sigma k times 18 choose 16 minus k 1/2 to the power of 18, and in the expanded form we have this expression, and if we actually calculate all this, we obtain 7.00007629, which is approximately 7. So we can say that on average, it is expected that 7 players will survive in this game. Also, in case you haven't noticed, this expression for EX is exactly the sum of the probability PKs, which was the cumulative distribution function. I am not going to explain the reason in detail. You can just check for yourself using this previously obtained expression for PK. Anyway, since EX is equivalent to this sum, we can also use our previously obtained probability table and simply add up the probabilities to obtain the same result. And with that, I think we have done enough with the game featured in Squid Game. Of course, we have only handled a specific case, and we have not considered other cases like when the number of players is greater than the number of panels that need to be crossed. But this video is already long enough, so I will not handle that case here. In my next video, I will return with regular problem-solving style video. So until then, take care, and thank you for watching my video.